Okay, so we're going to continue our discussion on topic 7 today, and we're going to start off with example 5 and do a couple more shear and moment diagrams. Okay, so we were doing the equation method and the graphical approach, and so now we're going to do another example here where we are going to consider the equation method but also use the graphical approach while we're doing that. So the goal right here for this example is to draw the shear and moment diagram for the beam. And by now, from the previous examples and discussion that we've been going through, we kind of understand the relationship between the loading on a beam and the shear and the moment, right? The moment is the integral of the shear and the shear is the integral of the loading. So they all kind of go in this consecutive order. All right. So what we're going to do here is we're going to start by drawing the FBD. So I'm going to call this like point A. So we have an AX reaction, we would have an AY reaction, and we would have a BY reaction. This is point B. And here, to get the resultant of this triangular distributed load, we would take the area under the system. So we would have 1/2 times the base, which is 9, times 6, and we would get 27 kilonewtons. If we want the distance that this 27 kilonewtons acts from each point, we would have this portion, which would be 1/3 times 9, so 3 meters, and we'd have this portion, which would be 2/3 times 9, which would be 6 meters. Okay. To solve for the unknown reactions, we can go through equilibrium of the whole system. We can sum moments about point A. Counterclockwise is positive. We have BY times 9 meters away minus 27 times 6 meters away. Set that equal to 0. And we get BY is 18 kilonewtons. We can sum forces in the y direction. Up is positive. And we get 18 plus AY minus 27. The resultant equals 0. And we get AY is equal to 9 kilonewtons. Okay, now we're ready to go ahead and make our cut. And since we have one continuous load, we can actually make the cut at any point here, X, and we only need to make one cut. Okay, because we have this continuously changing load here, so we can't make a cut at every single point, but we can define this function. You can see the load here is linear. It's a constant function. Right? So we only need to make one cut to define that whole function in terms of X. Okay. So let's go ahead and make that cut. This is the beam. We still have the loading on top, so this is the loading. This is the triangular distributed load here. Excuse me. Sorry. We have 9 kilonewtons from the reaction AY. And this here, this cut, is made some distance X away from point A. And of course, whenever we make a cut, we expose our shear and moment. So we have Vx and Mx that we've exposed. And now the question here is, what is the magnitude of this triangular distributed load? So I'm going to pull back here so that we can figure this out. And I'm going to erase some of this, all this stuff here, so we can kind of take a better look at this triangle. So we have the outer triangle. We have this outer triangle here. And we know that the total value at 9 meters gets to 6 kilonewtons. So this height here, this length here, is all 6 kilonewtons, right? This here, from here to here, 6. We want to know what the value is at any point X. We want to figure out how we can find the point at any point X, right? So what we want to do here is we want to set up a similar triangle system, and we want to say, well, if this distance, some distance X along the beam is here, then can we use similar triangles to relate this small yellow triangle to the larger green triangle? So what we're going to do is we're going to say, this is basically the small little yellow triangle. We're going to say that the whole 6 here, 6, is to the whole length 9, adds to similar triangles, as this wx here, this little value, this distance, as wx is to some x. And if we cross multiply, we get 6x equals 9wx, and we get basically wx equals 2/3 x. So this value here is equal to 2/3 x. That's the total height of the triangle. Well, now if we want the resultant, which acts somewhere here, right, we would need to say that is 1/2 times the base times 2/3 x, right? So we end up getting, if we multiply all that out, 1/3 x squared, okay? All right, so now we can go ahead and we can sum forces in the y direction. And we have negative vx plus 9 minus the 1/3 x squared equals 0. And we can solve for vx, and that is 9 minus x squared over 3. And let's think about that result for a second here. So if we look at the load, we know the load here, this load, right? This is linear, it's a straight line. That's load. What is the integral of a linear function, a straight line? It should be a parabola or a second order. So something like x squared. So here you see a function of x squared. What should we get for a moment? Well, for a moment, we should be getting a function of x cubed. So let's see if we get that. Let's sum our moments about x, set them equal to 0, counterclockwise is positive. We have mx, the moment there, minus 9 times a moment arm of x, plus x squared over 3 times a moment arm of x over 3. How did I get the x over 3? Well, the distance from here to here, the resultant to the point, is 1/3 of the total x, so we get the x over 3. If I simplify here, I get mx is equal to 9x minus x cubed over 9, and that is the final function for my moment. And it's good because we got a cubic function here, which is correct because we know that if shear was a parabola or a second order function, then the moment has to be a cubic or third order function. Okay, now we can go ahead and plot our shear and moment diagram. So I'm going to actually use the space here to redraw everything. Okay. So we have our beam. And we have our loading on the beam. Here, this was 6 kilonewton per meter. We have 9 kilonewtons. And then our BY was 18. And we have 9 meters for the total length. And we have 27 kilonewtons for our resultant load. Okay, so now we're going to draw our shear and moment diagrams here. Here we have shear, moment. Our shear is in kilonewtons. Our moment is in kilonewton meters. And we're going to start here. We know that Vx is 9 minus x squared over 3. So here we're going to start, we always start the shear with the first value on the diagram. So that's going to start at 9. Okay. We know we have some kind of cubic function, And we know that at the end, one thing about our shear moment diagrams I should have mentioned, they always have to close, which means the last point on the diagram must be 0. Must close, which means must go back to 0. So if it has to go back to 0, and we know at the end we're being pushed up by 18, that means we need to end at negative 18. And we're going to follow the second order function, so we have some type of parabolic shape that looks like that. And then we get pushed back up by the 18 at the end, and that is our shear diagram. Now, let's go through this slowly. I know that this was a little bit quick, so let's kind of look at what's happening here. We have a value of 9 on our shear diagram here. But we know that the shear is the integral of the load. So we can actually figure out what the slope is here. The load at this point is 0 because this is a loading on the beam, like this loading, right? The loading starts at 0 and it ends at 6. So we have a slope of 0. And then we know here, at this point, we should have a slope of 6. Because we have a value of load at 6 here. Let me write that on the other side so it's not so crowded. Okay. And we know that we have some 0 point here. Okay, so I'm going to draw some lines now. I'm going to draw some lines for our moment so we can make sure everything falls in the same place. And for our moment, we have no moment here at this point, no moment. So we're going to start at 0. And we, of course, have to end at 0. And the value of our moment diagram, the value of the slope at this point here, has to be 9, the value of the shear diagram. So we need a slope of 9 here, and we need a slope of negative 18 here, because the value of shear is negative 18. All we have to do is connect those 2 points. And we know that we have a maximum, although it kind of looks funny because of the way I drew it, but we know we have a maximum here, because when the derivative is 0, the integral is max. When shear is 0, right? If we want to find what that M max is, let's go to our shear equation. And let's say, where does the shear equal 0? What X value does it equal 0? So we end up getting 27 equals x squared, x equals square root 27. And if we plug this in to our m of root 27, we end up getting 31.2. So our max moment is actually okay. And that is our final shear and moment diagram for this problem. Okay, so now we can get to the point where we're really going to define this relationship between our distributed load, our shear, and our moment, because we've been talking about it a lot, these derivatives and these functions here, but now we can actually formally define this relationship that we have between our shear, our moment, and our distributed load. Okay, so as the loading on our beam increases in complexity, the method that's used to solve for shear and moment diagrams that we've done so far becomes quite tedious. Okay, so we can use the relationship, this relationship from calculus in terms of derivatives and integrals, to kind of solve more complex problems in a simpler manner. Okay, so let's go ahead and take a deeper look here. What I'm going to do is I'm going to draw a beam with any variable loading on it. So when I say any variable loading, it can be any kind of variable distributed load like this. And typically the way we do our sign convention is up is positive, down is negative. So I'm just going to draw it up for a positive sign convention, because I want this to be as generic and general as possible when we're going through the derivation, so that we can apply this to any system. Okay, so this is our load W as a function of X. Okay, and we can also have some point loads on this system, so we can have some point loads. We'll call this F1, F2. Okay, and we'll have some points here. We'll have a pin. We'll have a roller. This is a simply supported system. We'll call this point A. We'll call some point here, let's say, some point B, some point C on the beam, and let's say this is point D. Okay, and let's even say we can have an applied moment here because we want to make this very general. Some applied moment on the system. And what we're going to do is we're going to isolate a little tiny differential element called delta x somewhere between B and C so that we can show this relationship. We're going to isolate some very tiny little element delta x, okay, where the distributed load is applied. And I'm going to kind of expand that here. So let's expand that. And this is kind of what that little dx portion looks like. We have the distributed load, right? And we have this width here that we've isolated. This little differential element has the width of delta x. And of course, on both sides, since we've cut this, we have shear, but we have V plus some change in shear because we have some delta x here. And of course, we have moment here. And then we have some moment here, which is going to be m plus delta m, some change in moment. And we have some resultant F equals W of x times delta x, the change in x. Okay. And if we look at this distance from where the resultant acts, it's some portion, right? Because this is the centroid. It's some portion of delta x. So some k times delta x, some fractional distance of delta x where k has to be between 0 and 1. So like it could be at 50%, 40%. Okay. If wx was uniform, k would be a half. So now we want to apply equilibrium. Okay. And we're going to go ahead and sum forces in the y direction. And we end up getting V plus W of x, delta x, minus V plus delta V equals 0. And if we divide by delta x, we end up getting, let's go ahead and put the delta x in. Actually, let's simplify. Let's simplify before we divide by delta x. Let's simplify this a little. We end up getting delta V equals W of x, delta x. Now let's divide everything by delta x. Divide that over. And we end up getting here delta V over delta x equals W of x. And then we can take the limit as delta x approaches 0. We get the derivative here. We get dv dx is equal to W of x. So this tells us the relationship between the load and the shear. This is super important, so I'm going to highlight it, put it in a box, right? So what does this tell us? It tells us that the slope of the shear diagram, this is the derivative, right? The slope of the shear diagram is equal to the magnitude of the distributed load. This also tells us, we can rewrite this as delta V equals integral W of x dx. And this tells us that the change in shear is equal to the area under loading curve. These are some very important observations that are going to help us draw these diagrams. Okay. Now if we continue going through this, right? We still have this diagram that we're working on. And let's continue applying equilibrium. And let's go ahead now and take the moment. Let me copy this. Okay. And let's now take the moment. Let's say this is point O. Counterclockwise is positive. We have m plus delta m minus wx delta x k delta x minus v times delta x minus m equals 0. And we can simplify. We get delta m equals v delta x minus kw times x times delta x squared. Actually, x squared. And if we divide by delta x again, we end up getting delta m delta x equals the shear basically. And if we say delta x approaches 0, we can turn this into dm dx is equal to the shear. And we knew this previously, we're showing this. And what this tells us is, well, let me highlight it first. What this tells us is the slope of the moment diagram is equal to the shear. Right? And if we continue this, we can solve for delta m, and that is equal to the integral of v dx. And this here is the change in the moment. Is equal to the area under the V diagram, which is the definition of the integral and the derivative. Okay, where can we find our m max? This is also super important, right? This happens where dm over dx equals 0. So basically when shear is 0. Okay, now one thing to note here before we get to the sign convention, note this is very important. These relationships do not work for point loads or do not apply to point loads. Only distributed loads. Why? Because point loads cause discontinuities. They're abrupt changes. We deal with them differently. Okay. Now, for our sign convention, we're going to assume these are positive. Change in shear is positive. Then the V diagram jumps up when F is up and vice versa. So here is our positive sign convention. Okay. Same goes for moment. We have this rotation in this direction causing this concave up relationship. This is a positive moment. Concave down would be that negative moment. Okay, so we're going to go ahead and go through another example now, and we're going to draw the shear moment of this system. Okay, so let's go ahead and take a look here what's happening. Now we kind of have an idea of both of these methods that we're using, so I'm going to list out the options here. We have option number 1, and that's to make cuts to solve this. So if we wanted to make cuts, along the beam, we need to figure out where the discontinuities are. So we'd have to, if we're walking on the beam in this direction, we'd have to make a cut here, keep walking. Oh, well, we have a discontinuity. We have to make a cut somewhere here. So we would need 2 cuts. Option 2, use the relationship between W, V, and M. And this is basically the graphical approach. Okay, this is the equation. So I'm going to go with option 2 because it's typically easier when you have to make multiple cuts to kind of go through option 2 if you can. You can get away with doing the equation method, okay? So let's go ahead and redraw this system. Let's redraw the system here. I have a 2 kilonewton load, and I have a distributed load of 1.5 kilonewton per meter. So what's going to happen, and this is 2 meters here, 2 meters here. I have reactions. Oh wait, actually, I have a cantilever system, so my only reactions are here actually. My By is equal to 5 because this resultant here, 3. And my MB at the end there is equal to 11. Let's go through that process here. So we can sum forces in the Y to get that By like I got 5. We get By minus 3 minus 2 equals 0. We get By equals 5. Some moments, we get negative MB plus 3 times the moment arm of 1 plus 2 times the moment arm of 4, and we get MB equals 11 kilonewton meters. Let's go ahead and draw our axes now. And we have V in kilonewtons, M in kilonewton meters. And we're going to go ahead and go through this one by one. So let's start with the shear here. At x equals 0, at the first point on the beam right here, I have 2 pushing down. So I'm going to go negative 2. That's going to push me down, initially negative 2. Okay. For the first 2 meters, from here to here, I have no change in the shear. So let me go ahead and draw a line here so I can see where that discontinuity ends. Okay. So until that orange line, I have no change. When I get to the orange line, what happens is this is a constant distributed load. Right? So what is the integral of a constant? It should be a line. Right? A straight line with a constant slope. So this line that I'm about to draw should have a constant slope, right? So the line with a constant slope of 1.5. Okay, or negative 1.5, right? Because it's going down. So I'm going to draw the line from here to here. And I know that it has to go down too because at the very end here, at this point, I drew it a little too far, so let me fix this. At this point here, I have to be pushed up, back up to 0 by this 5, right? So this has to end at negative 5 so that the By can push me back up to 0. And this is my shear diagram. Now, I can look at this shear diagram and get really easy values for my areas. So the area of this first box 1, I can get the area of 2, I can get the area of 3. The area of 1 is equal to 2 meters, right? This is 2 meters times a value of 2, so 4. This is also going to be 4, right? This area is going to be 1/2 times if this is 4 and the whole thing is 5, then this has to be 1 and 4, right? So this area here area 3 has to be 1/2 times 1 times 2. I'm sorry, this is 2, not 4. Maybe something looked funny. This is 2, right? Sorry. 2 and 3. So 1/2 times 2 times 3, which gives us 3. Okay. Why am I getting the areas? Because they're going to help me plot my moment. I know that I need to start at 0, and then I know that I have this moment here, 11, that needs to push me back up at the end. So I know I need to end at -11 to push me back up to 0. Okay, but what's going to happen in between here? So I know that the value of my moment at this point here, the value of my moment at the orange line needs to be equal to the area under the curve. That's the definition of the derivative. So this area that I just highlighted is equal to 4. So, and it's below it's actually -4, right? Because it's a -2. So I know that the moment value has to be here, the initial starting of 0, I need to be at -4. How do I get there? Well, I have a constant, I have a 2 meter, a -2 constant value of shear here. So I need to get there with a straight line. Here I have a straight line. I'm going to highlight this in right? For that blue area, I have a straight line. So I know that this has to be a curve. And the curve is going to start out with a slope equal to this value here of 2, -2, and end with a slope of -5. So it's getting more negative. So it's going to be -2, more like -5. So I'm just going to connect. It's a little bit too much. Let's see. Something like that. And does it get to -11? Let's see. So I start at -4 minus, what's the area here? Minus the 4 minus the 3. That is -11. So it all closes. I'm at -11. Then I get pushed back up by 11. And so everything is good. And I have all of my values on the moment diagram. So the best way to understand these is to try practicing them on your own. So we're going to stop this video here. Make sure you retry these problems on your own and everything makes sense. And then we'll move on to the next video.